Well, it's good to be here. First presentation live to DConf in several years now. I've missed it. So, how many of you guys are local? I guess the rest are international. How many from the US? Good chunk, and I guess, hi, Ali. Yeah. I guess a lot from Australia, Germany. Lots of fun stuff. Well, D has a lot of features in it. And lots of times the features combine in ways that are unexpected. And myself and a lot of the people who work on D have discovered various things, combinations of features that are kind of fun. Okay, so what I'm going to do is sort of present a grab bag of these combinations of features and fun things you can do with them. You know, sort of like, coffee and chocolate. One of those great discoveries you'd never think they go together, but they go together brilliantly. So we've things like octal literals, how to do zero terminated strings without allocating any memory, which is fun. Voldemort types. Some of you already know about some of these things, but I still thought I'd collect them all together because I don't know who knows what, and I thought I'd just list them all. Using chains to avoid memory allocation. Memory allocation is always a big risk in programming because if you make any mistakes, you wind up with memory corruption. So, and also you can, of course, run out of memory, which is never good in your program. So finding ways to avoid doing memory allocation is usually a nice win. Dealing with errors is always a big problem. And there are many ways of dealing with errors, and I'm going to show a way that sometimes works. It's worth investigating to see if you can make it work, to deal with errors without having error codes and without having exceptions and without explicit error management, which are the usual ways of doing it. D supports gotos, well, for two reasons. One, because C does. And also, I like gotos because gotos provide control flow that is not necessarily available in the usual high-level or structured programming constructs. And I found things you can do with nested functions to avoid this problem. Windows never just lets go. We have the technology. We can do things like half floats. I think this was a request by Manu. Is Manu here? There he is. You remember half floats, right, Manu? Another way is using compile time function execution to statically initialize things. Here's a recent one, using enums to generate a scope list of names. And what can you do with a scope list of names? We'll get into that. And then a rather surprising discovery that I almost couldn't believe existed is a way to interface 2D from C. Normally you talk about interfacing 2C from D, but what about the other way? Well, let's start out with octal literals. C, C++, other languages in D support an octal numeric literal, and D doesn't anymore. And why doesn't D do it anymore? Octal has a history going back, I'm sure before the PDP-10, but PDP-10 was when I encountered it. PDP-10 has 18-bit words or 36-bit words, and that's naturally divisible by 3. So octal turns out to be a very nice number base for programming on the PDP-10. Of course, PDP-10 is long since obsolete. Existing 10s are in a museum now. But Octal lives on. But it turns out that Octal is really only used for one thing and one thing only, and that's file permissions. And with file permissions, the Unix file permissions are based on Octal. And you have, let's see now, 3 digits to it. You have the user permissions, the group permissions, and the world permissions. So that gives you 3 digits. And having Octal is still nice for that because quick, without using your computer, what is 755 in decimal? How many of you people know it? That? Nobody does unless you're one of those intuitive math people, which I certainly am not. I don't know what that is in decimal. So one thing we found with template syntax is you could do literals with it. And so up at the top, you have Octal bang 755. Now, which actually is 493 decimal, and you'll realize that I'm sure you'll agree that 493 has no resemblance to 0755, and this is kind of a horrible thing to have in your code, 493 magic number. What I found with templates is I was just thinking of templates only for structs and functions. Well, it turns out that you could do templates for any other symbol, including enumerated types. But an interesting thing about that is the 755 is actually not an octal. It's a decimal number. So what is the magic to make that work? And the magic is you do enum octal, so that's your template octal, and it converts 755 from decimal to octal through this recursive function. Now, this actually exists in the Phobos runtime library. And there are a couple special cases in it, like all these examples here, I've kind of compressed the code down to the minimum so it doesn't deal with special cases. One of the special cases is if the number is too large or not large enough. Misspoke. The number would be too large in decimal to express all the digits in an octal number. So you kind of have to special case that out. And the professional implementation does that, but this is the root of the thing. So the advantage of it extends more than just octal. D used to, how many people know that D used to have a binary data type? You can tell all the old timers here. I thought it would be great to have a binary data type, and it turns out to be, in practice, completely useless. And the reason I say that is because once you get used to hex, you don't need to see the binary bit patterns anymore. And the numbers get really long in binary, so you can't tell what they are anyway. It's just more convenient to use hex. So we dropped the binary literal syntax, and ironically, we dropped it, and then C++ apparently has picked it up, and other languages have picked it up too. But we're not going to, because we can just do an octal thing, support binary numbers just like we supported the octal one. Don't need to extend the compiler, which is really important, because when you have a need for a special numeric type, you can create it in D without, like what Manu did was send me emails saying we needed to support half float in the compiler. I'll get into half floats later. Another common thing is D has length delineated strings, whereas C has 0 terminated strings. And it's easy to take a C string and turn it into a D string because you just do a Stirling on it and you've got the length and you're ready to go. But going the other way requires appending a 0, and that's going to require an allocation. This is just a nuisance. Because why would you want to do an allocation just to add a 0 onto the end, and you're just going to do one little thing with it, like do a file lookup or open a directory or something like that. So we want to do it without allocation, and we want to allocate the 0 terminated string on the stack. But the problem is D functions don't have a way to allocate or put things on the stack and then return the memory you allocated. Because once you return your stack allocated memory, it's off the end of the stack, and it's in Never Never Land, and it's memory corruption to even attempt to access it. But there is a way. I did not discover it. I don't know who did. Perhaps the person who did can raise their hand, but a way to do it without, we can allocate it on the stack without these problems. And people who work on the compiler know this function as toCstring then. And it takes 2 arguments, a delegate. Now it's important to note there that the delegate is passed by name, not by a value. And there's the string you want to append a 0 to. So how it works is really kind of clever. You find the length that you need for the 0 terminated string. You allocate a buffer on the stack. And then in DMD, there's a type called a small buffer, which is just you give it an array that it can use to fill things and a length that you're going to use. And here we initialize it, add a 0, and then return GG a pointer. Now, how can this actually work? Or what is happening here? Well, the traditional way is you create the string, add a 0 to it, and then call a function that does something with it. Well, what this delegate does is the function that does something with it is passed in. So this becomes on the stack. It does not return it. And the result looks like this. So our name is our string. We call toString then. And here's the code we want to execute on the 0 terminated string. And because it's being executed in the context of the template, it's not a pointer into an expired stack frame. It's a pointer into a living stack frame. So I think this is a very clever thing. I wish I had thought of it.
And no dynamic memory allocation for the delegate, for the context?
That's right.
Okay.
There is a fly in the ointment. You'll notice that the buffer has a size of 512. That's how much you get on the stack, which, 512 ought to be enough for, anyone. But that's why it's small buffer. A small buffer will allocate and free its own memory if it exceeds the buffer size. So it will still work. So in the rare case where somebody actually needs more than 512 bytes, it will still work. But most of the time, the strings you pass to C functions that need to be 0 terminated. In fact, nearly all the time, 512 is plenty enough, and you won't have any memory leaks, and you won't consume any memory with this. Okay, Voldemort types. I was looking at, well, we decided to add the auto return type to functions, so didn't really have to specify what the return type of a function was, which turns out to have some very interesting consequences. Because if you want to return a struct, you don't have to declare the struct outside of the function. You can declare it inside of the function. And so here we have a struct declared inside of the function, and what it does is it produces a range. And the range, a range has a beginning and end, which is I and j, and then the three functions you need for an input range, empty, front, pop front, and returns it. And it's called a Voldemort type because the caller does not have access to the name of it, so it's the struct that can't be mentioned. It's a chunk of data that has certain capabilities. In this instance, the abilities are the empty front, pop front. You can use it as a range for each x, a range from 3 to 6, print it out, and there's your result. So what this enables you to do is to encapsulate your custom data object in a very neat and succinct manner and writing very little code. Me, I kind of like to encapsulate things like that because I don't like the names of what I'm working on spilling out into the rest of the program, and this keeps it nicely encapsulated. Another thing we do with memory allocation, and I've programmed in C for a long time, and one of the common things you do is you construct file names, paths, and you deconstruct them and you recombine them. And it's always a constant zoo of allocating memory and copying memory. And with that constant zoo, I found that there's almost always a rich source of bugs in it. Now, we could just concatenate things like done on the last line using the garbage collector, but sometimes this is a temporary storage you need for this. Do you really need a garbage collector managing the memory for you that may persist for a while? You want to just use it and be done with it. So let's see if we can do better. And here's the no-allocate way, is we use an algorithm called chain. And chain will take the path, name, and extension, and it will return an object that is not the concatenation of the three strings, but is a container holding the three strings, an object that contains the three strings. And how that works here is, oops. It turns out that the object is actually a range. Well, it's an input range, which has the usual empty pop front and front. So WriteLine knows about input ranges. So if we chain it and then we pass the chained object to WriteLine, it knows how to figure it out, and it will print that. If we take the chain and we access it by character and store it in an array, then we're actually allocating memory, and it prints the same thing. But it turns out, if you look at the implementation of the std.path, std.path does a lot of file name manipulation, assembling paths, dealing with extensions, replacing extensions. And it doesn't actually return strings, it returns ranges. And so the whole thing operates without allocating memory. And here's the link to the documentation of where the chain is. Not many people use chain. I think it's one of the most underappreciated tools in the Phobos standard library. But by using it to avoid allocating memory, chain is ideally suited for Voldemort types. Everybody hates dealing with errors. And what happens when everybody hates dealing with errors? They don't. Yeah, they just ignore it. Like, how many people have seen printf hello world without checking the error return of printf? I'll raise both hands because I do it all the time. And I know it's bad, and I know you're not supposed to do it, but putting in that error checking code is just awful. The C++ way is exceptions. Exceptions are sold as a zero-cost abstraction, but it's not really. It has costs for your optimization and in particular your code size, and also complexity because it introduces a lot of code paths through your code that you might not be anticipating. We already talked about error codes. The current thing is to use optional return types, which might be an error or it might be the data you're looking for. I haven't used them myself, but I've heard complaints about them that it's messy and ugly to deal with optional return types. So one way to avoid returning errors is to define the error out of existence. So there is no error return. Can't always do that. But one easy example is I'm searching for a substring in a longer string, and what do I do if it's not found? Do I issue an error message? Do I return some magic number that I have to check for? Do I throw an exception? Do I do an error code? No, you just define a zero-length string as being didn't find. That's a simple one. Now, here's a method that I often struggle to explain this to people. I think it's a brilliant idea. It's the NaN method, where one of the floating point bit patterns there is called a NaN type, which means not a number. And there are lots of floating point operations that are invalid. For example, divide by 0 is invalid. And the result of that, instead of throwing an exception or returning an error code or anything like that, is the return value is NaN, the NaN bit pattern. And that's silent. And any operation where one of the operands is a NaN is also a NaN. So what happens is the NaN bubbles up in your code to the top level where you print it out and it says, the money in your bank account is NaN. You had so much money you overflowed the bank system when you get that. And you got NaN. The problem is then you have to go find where it happens. But what I was told by somebody who worked on satellites is sensors in satellites have it's a giant matrix of pixels, okay? And as with anything else, you develop bad pixels over time. Your sensor degrades and it starts developing bad pixels. And what most people will do is for a bad pixel, they'll just return 0. The problem with 0 is you don't know if the sensor value is 0 or it's a bad pixel. But if you program the bad pixels to return NaN, then you know how degraded your image is when you get it. And also any calculations you do or any image enhancements you do to your sensor image you'll see nans in your enhanced version rather than having like 0 averaged into the other data points, essentially ruining your data in ways that are not obvious. It is part of the IEEE 754 specification. And like I said, a lot of people don't like it, but I think it's brilliant. It also makes the code free of a need for error checking. Okay, a variation on nans is used in the decompiler. One of the problems with a compiler is when you do have an error, then you have to kind of get the compiler back on track so it can continue to parse and find more errors, because you don't really want it to quit on the first error it sees. You'd like to gather up all the errors at once and then correct them all at once and then run a compiler again, especially if it takes the compiler a while to run. So the earlier decompiler used to try to do error recovery, which is, try to guess what the user meant and patch the ASTs and continue on. And this really never worked very well. You wind up with a lot of weird cascaded error messages because what it guessed was not what the user intended, and it would cause further errors. So I took inspiration from the nans, and the AST node where an error message was emitted, there's a error node, and it is replaced with an error node. And any AST node that has as one of its subtrees, if one of those subtrees is an error node, that AST node also becomes an error node. And this worked out great. The error messages most of the time, or far more frequently, are accurate and they're not cascaded garbage error messages. So, and it also makes the code simpler too, because on the children of your node, you just look to see if they're error nodes, if they are error nodes, and if they are, you just return another error node for it. Now the replacement care variation is another way of doing it. And it was something we learned over time, because when D was started, we thought, well, when you run into invalid UTF code, you throw an exception, because you really want to know if your Unicode is invalid. Well, it turns out you don't want to know if your Unicode is valid, and you don't want to throw an exception, and you don't want to quit. For example, if you're a web browser and you want to render the guy's text, you don't want to just throw an exception if somewhere in there there's some bad Unicode. What you want to do is still display the good Unicode in a reasonable manner and do something reasonable with the bad Unicode, or the bad code points in there. In other words, quitting is undesirable. Now, my solution, if I was running the world and running Unicode, would be to define all of the Unicode points. But of course, they didn't do that, and there are lots of malformed Unicode points in there possible. And it turns out a better way to deal with it is there's a special Unicode character called the replacement character, which you just take your bad Unicode and replace it with a replacement character, and then all you have to do is the replacement character is usually rendered as an empty box. So you don't really have to do error checking in your code, your Unicode. You can still just continue to process it, and some of your bad Unicode will just show up as a box in there. So it's another way of doing nans. On to more fun things. I used to write code like this all the time. And I wrote it because it's compact and it's efficient. And I wanted that. And you'll still find a lot of code like this in the front end of the DMD compiler. But one day I realized that nested functions can replace it. And it turns out much nicer. You can create some nested functions there, continues on, and instead of doing the goto, you call to combine common code and have common tails for things. You just call one of the nested functions. And you might say, well, that's inefficient. It turns out it's not inefficient because compiler optimizers are able to inline those functions and pretty much produce your goto code that you had before. So this is a cost-free way of getting rid of those goto codes because, you know, I have a bad habit of creating very long functions, and when I see goto L3, I scroll down and I scroll down and I scroll down. Eventually I find L3 and then I forgot where I came from. And the indentation, I don't know what happened with the indentation level, things like that. So I've been gradually converting to using nested functions instead, which makes the code a lot more readable and maintainable and, frankly, more hygienic. Okay, now to Manu's favorite topic. I'm blaming you, Manu, I'm sorry. I'll make you pay for coming to this conference. It turns out in game development, 32-bit, well, floats come in three varieties. There's 32-bit, 64-bit, and 80-bit, which is sometimes 128 bits. Well, it turns out that games and graphics and all that have very large quantities of graphics, which they represent with floating point numbers, and they don't need the accuracy. So what's commonplace is to use a 16-bit floating point type called a half float. The 16 bits cuts the storage requirements in half, which makes your code run faster. It was requested as a built-in type by Manu. And the trouble with it was everybody has their own notion of what a 16-bit float should look like. So there's no standard on it. There are several competing formats, each with their adherents. And wiring them all into the compiler is not practical. So let's see if we can do something with what we now know about combining D features and do something better. What we'd like to use is recycle that Octal discovery and create a half float literal, which looks like this, HF, bang, and then we give a floating point constant to represent the half float literal. And if you do math on two half floats, it actually produces a full-size float. So if you want to get it back to a half float, you have to do a cast. And you can also cast another floating point constant to a half float. So it's not quite a built-in type in that the implicit conversions you're going to have to do yourself. Here's the format I picked sort of at random. Got it from Wikipedia. The image is from Wikipedia too. So our implementation strategy is to store the half float as a short, which is conveniently 16 bits, implicitly convert half floats to floats, and explicitly convert, meaning a cast, a float to a half float. Here's all we need, really, is we need a short to float function. We need a float to short function. Here's our member, which is the storage, which is the exponent mask ORed with 1. And we statically initialize it to a nan. There's that old nan thing again. And the alias this in there means that whenever the compiler doesn't know what to do with this. It converts it to float and uses floating point arithmetic on it. Now, floating point types have properties, and here's all the properties and their implementation. You have the number of digits, mantissa digits, max 10 exponent, and those can be done as enums because they're integer values. You can't do enums for a half float type, so those are inline functions which get inlined and go away in your actual runtime, and they're all implemented there. So you have infinity, nan, max, and epsilon. So we get here's our implementation of the half float literal, which is pretty trivial. And the code to implement the floating point conversions is a little long for the slide. So there's a link down there to where it is. And the cool thing about it is, how many people know what a guard bit is? 2. How many people know what a sticky bit is? A little more, 4 people. How many know what a hidden bit is? And how many know how they all work together? Nobody knows. What?
This floating point math isn't real.
Isn't real, yes. It's only ephemera. But anyhow, there are very rules for doing that, and the rules are actually pretty simple, except that nobody ever cares to explain them to anybody. I implemented floating point arithmetic to support CPUs that don't have a floating point processor, so I was forced to learn all this stuff. But anyhow, you've got it easy, because the half float implementation at the link there will show you how all those overflows, underflows, sticky bits, rounding bits, all that stuff is correct IEEE arithmetic. And Max Houghton was working on an 80-bit floating point emulator, and he didn't know how to do this stuff, and I just pointed him at that and says, there you go, that's how you use those extra bits to get all the correct rounding. So Max, are you here? There he is. So now, Max, you got no more excuses. It's all laid out for you how to do it. It's going to be perfect, I know. Okay, here's another fun thing. Initializing arrays, and once again, I want to say these examples look trivial, but I'm trying to illustrate the concept. In reality, things are much more complicated. But they don't fit in the slide, and I don't want to make you sort of read a bunch of irrelevant fluff to figure out how it works. So let's say we need a static table of squares for speed, and here's how we initialize it. How many people know that 19 squared is 361? Not me. How many people can do it in your head? Yeah. You can? Yeah? I know this is the right crowd. I'm not that quick anymore with in my head math. But anyhow, pity the poor QA guy who has to review this. He's got to know that 19 times 19 is 361, and the odds of him making a mistake are high, and more likely he'll just skip over it and go, he knows what he's doing. Okay, here's the old way I used to do it, is I would actually write a program to generate C code and later on D code to generate the table. And you can still see vestiges of that. I think it's all been finally removed from DMD, the compiler. The compiler, people who've worked on it for a while know that it was actually a 2-level compiler. First, it compiled these programs, which were then run and generated all the complicated tables. And then you'd run the real build of the compiler, which would use the generated tables. And this is basically how it worked. Pretty simple. Of course, the way D was using it was much more complicated than that. The new way is a wonderful, chocolate and peanut butter thing you can do with lambdas and CTFE that I never thought of. I don't remember, I think somebody else was doing this, and I looked at it and I thought, oh, that can't possibly work. And I tried it, and of course it did work. So what we do is we're going to statically initialize squares. And this double paren means a lambda with no parameters. And in the lambda, we statically allocate an array. We fill the array with squares, and then we return our static array. And these parens here mean execute. And this all happens at compile time. And I thought, well, I better check the object file and see if that lambda is in the object file. And it turns out a fix made to the compiler not too long ago, I can't remember who did that, but functions that weren't referenced in certain ways where the code was not generated for them. So you get this for free. It doesn't cost you any code at runtime, it doesn't cost you any code embedded in your executable. And this is, yes? Somebody had a question? So this is a real nice feature that combines multiple features of D to make it work. This one is Dennis Corporal. He came up with this idea. I kind of modified it somewhat. In order to support C with the import C compiler, I had to support bit fields. And in supporting bit fields, naturally it came, well, why don't we use bit fields in the DMD source code, because we were always having Boolean flags in the various data types that consumed an unreasonable amount of memory. So I wanted to add bit fields to D too. And Dennis goes, well, no, I can make it work using templates and introspection and all that, and he did. So let's say we have a struct and we want 3 bit fields in it. And to get bit fields in D without bit fields, what you have to do is create a bunch of property functions. Now, who wants to be the QA guy who has to read that and determine if it's correct? Yeah, I see you're laughing, derisive laughter. You know, I pity the poor QA people who do this. And so I'll show you a better way, or actually Dennis will. Dennis's version was slightly different. He would have a struct flags, and then he would go bool square, bool circle, bool triangle. But I kind of thought we can eliminate the bool on that, because all we really need is a list of names, and names that are in a scope. So this is, we can sort of hijack the enum construct to give us a list of scope names. And the idea is we'd rather write code like this, where we give our list of names and mix in, generate the flags. And there's our unit test down at the bottom. I'm kind of an abbreviated set of unit tests for it. And here's the code to implement it. And I compressed it a bit and took out some special cases and some error checking so it would fit on the slide. But that's really what it is. And who thinks it looks horrible? Unreviewable. I agree. It looks horrible. But you only have to get it right once. Okay? With the previous one, you know, the property of writing the manual thing, you have to get it right every time. And I don't know about you, but I make typos and I transpose digits and I do all kinds of things. This thing, I only have to get it right once. Oh, I think we're out of time. Should I accelerate or keep going?
Keep going.
Keep going? Okay, thumbs up. We're going to keep going. Okay, we don't have too much left anyway. Imports in C. Well, I couldn't resist, and I gave a whole presentation on this in the last year about adding imports to C, and this is what it looks like. We can import Studio, stdio, and then printf hello world, and it will work. It's not even D, it's actually C. And, you know, I was out jogging one day, and it occurred to me, what if the module's a D module? What if I imported a D module? What is going to happen? And it turns out this was no additional code in the compiler. I tried it, set up a little module that, you know, a function in there. I can call the function and it works.
That's C program, right? The top one.
No, that is a C program. This is a D module on bottom. So here we have a C programming, a C source file importing a D module and accessing it with C syntax, of course. Can we do overloaded functions? Somebody tried that on in the forums, I don't remember who, and said, hey, it works. You can have overloaded functions in C just by having an overloaded function in your D module. Now here comes the big test. Do templates work? And I'm happy to say templates work too. You can actually use templates from C. As long as you can express it in C syntax. So I thought that was a very kind of a fun thing to do because it completes the circle. It's not just D interfacing to C. If you have a project that's mixed C and D code, you're going to want to have your C code calling D code too. Now you can do it. And of course, the whole is more than the sum of the parts. When you have a bunch of complicated things, they can combine in unexpected and fun ways. And sometimes you make a really nice discovery that makes your code nicer. So like Dennis's discovery of how to do bit fields. Now, I've since added bit fields to D because I was just bound and determined to have bit fields in D, but I can't deny what a great thing Max did by Dennis, I'm sorry. What a great thing Dennis did by figuring that out. Okay, AMA, questions?
Yeah, I think we can do one or two questions, and then we should let everybody have a break. So, yeah, thank you, Walter, first. Now, who has a really good question?
Come on, now's your big chance.
Sorry, I have a short question.
Is it a really good short question?
I hope so. On one of the slides, you were talking about making use of allocating on the stack a zero terminated string, and talking about how it can be used as ranges for everything all the way through. And you give the example of WriteLine, which is able to use it. But don't you need to do a memory allocation when you actually make use of the system as use of the data as an actual string, like opening a file from the operating system?
Okay, that is a great question. Okay, if your application that you want to send it to supports ranges, you never have to allocate memory. But if you're going to pass it to C, C doesn't know anything about ranges, you're going to have to allocate memory. And see if I can find the slide there. Okay, here we go. So here, you don't have to allocate memory because the right line knows about ranges. But if you're calling a C function that takes a zero terminated string, you're going to have to allocate memory and turn it into a string. So this construct here, the bychar and dot array, will walk the range and turn it into an allocated piece of memory. You could probably also on this use the zero terminate and then execute code thing I also showed you to avoid the allocation as well.
All right, cool. Should we do one more? Yeah, it's going to be really quick though.
So I think it was a slide back or something about the C temp string then function.
Oh, to C string then.
Exactly. Could it have also worked if you used name value return optimization?
No. No, because with the name value return optimization, the caller needs to know the size of the memory being allocated. It needs to know the type that's being returned.
Yes, but the small buffer was 512, right?
Yeah.
Of course, it's not going to work if it's larger, right? But
Well, that's what I'd often do, but it pushes the logic into the caller. And that's what I was trying to avoid, is having all that logic in the caller. I would like to encapsulate it so I don't have to repeat the logic all the time. So that's the big advantage of this, is I just call toC string and then call that C function. I don't have to write the machinery or put that machinery in the caller. It's all down, it's all encapsulated down the stack or up the stack. Depends on your perspective. So yeah, that's the reason for it. And this has been used a lot in the source code to the DMD compiler pretty successfully. And I was initially skeptical that this isn't going to work out too well, but it worked out great, and I was wrong. It's one of the times I was happy to be wrong.
All right, and that is all that we have the time for today. So thank you again, Walter.